Thank you very much for the invitation to come to this conference, and it's very nice conference and nice place. And my talk today will be about neutron stars beyond general relativity. Okay, so theories beyond general relativity have many motivations. For example, the lack of enough observations in the strong field regime, the dark energy, dark matter hypothesis, quantum gravity string theory, and so on. But the question is that even if we are convinced that general relativity should be modified in one way or another, then the next question comes, how should we actually do this? And a good starting point here is the Lovelock's theorems, which says that Einstein field equations are unique if we are working in 4 dimensions, if diffeomorphism invariance is respected, if the metric is the only field that is mediating gravity, and the equations, the field equations, are second order. If we violate any of these assumptions, then we deviate from general relativity in one way or another. In the present talk, I will focus on, especially on theories possessing an additional scalar field. So even though it might seem very restrictive and you might think that this includes only scalar tensor theories, for example, this is not so. And for example, quantum gravity motivated Gauss-Bonnet gravity or Chern-Simons gravity, they possess an additional dynamical scalar field. In cosmology, we know that ultralight axion dark matter can be described effectively with scalar field. We have scalar fields in inflation, FFR theories of gravity, for example, are equivalent to a certain class of scalar tensor theories, and so on. So practically the theories possessing scalar field are much more general than perhaps originally thought. And you can ask, okay, why scalar field? Why not other fields like vector or tensor fields? Well, the truth is that indeed it's possible to use other type of fields, but in practice, it turns out that in many of cases, even if you are able to build a self-consistent theory, build a neutron star, or sometimes even black hole solutions in these theories, they possess certain severe instabilities, and the picture doesn't work as nice as for scalar fields. Okay, so imagine that we have at the end chosen our favorite theory of gravity, and we would like to build compact object models in this theory of gravity. Then if we want to build neutron star, we hit immediately the first problem. And that is that there is a degeneracy between equation of state uncertainties and modified gravity. And here is one example of this. So this is mass of radius diagram for neutron star solutions. And the black lines here are the GR solutions. The red lines are neutron star solutions in the so-called FFR theories of gravity. And the different pattern corresponds to different equations of state. So if we choose one point here, we can hardly know whether this is GR with a Sly equation of state or whether this is FFR theories of gravity with the APR equation of state. And this is the degeneracy I was talking about. So in most cases, when building equilibrium solution or even when studying dynamics, we have this type of degeneracies, and practically we have small qualitative deviations from general relativity. Oh. And something that I'll talk about at the end of the presentation is that it will be actually great if we have at least a set of theories of gravity where instead of small qualitative difference, we have this more specific qualitative difference between GR and another theory of gravity that are much more easier to trace and to that are much more easier to trace in the observations. Okay, but now let's start with the models of neutron stars beyond GR. And first I'll start with the models that with the so-called spontaneous scalarization. And apart from the fact that this is, well, my favorite mechanism of developing scalar hair around neutron stars, the truth is that, at least for neutron stars, most of the literature for the astrophysically relevant neutron star solution or astrophysical implications are about the scalarized neutron star in the Damour-Esposito-Farese model. So this is the widest studied neutron star model beyond GR up to date, and that's why I'll talk a little bit more about it. Okay, so what is the idea behind spontaneous scalarization? So the general idea is that we should have a modified theory of gravity, of course, that possesses an additional mediator at gravitational interaction, a scalar field. That is clear. And the most important is that we want to design the theory in such a way that it is perturbatively equivalent to general relativity. This means that all GR solutions are also solutions in this bigger theory of gravity, but we want a mechanism that allow for scalarization, that is development of the scalar field when we reach a certain threshold of the compactness of the space-time curvature or something else. Okay, and how do we build such a theory? I will start with the simple scalar tensor theories because this is the first theory when this mechanism was developed a few decades ago. So how do we build a scalar tensor theories? Okay, so let's start with the GR action and with the standard matter part, and then let's add a scalar field. Okay, how does it look like? So when we add a scalar field, normally we have to add a kinetic term of the scalar field, a potential term, and since this is scalar tensor theories in the Einstein frame, we also add a coupling term in the matter action with the scalar field explicitly entering here. Okay, so remember that I told you that we want this theory to have always GR as a solution of the field equation. This means that phi equal to 0 should be always a solution of the field equations. But we want these GR solutions to destabilize. In the case of neutron stars, in scalar tensor theories, they destabilize when the compactness of the star reaches a certain threshold, and the mechanism for destabilization is natural to come from the scalar field, right? And this, so then let's isolate the field equation for the scalar field, and let's analyze it. Okay, and so this is how the scalar field equation looks like. And here, this alpha phi is just our previous coupling function. And T is the trace of the energy momentum tensor. So we want, in certain point, the scalar field to become unstable and to grow above the phi equal to 0 background. Okay, so how do we derive a criteria for this? So we can take this equation and perturb it with respect to the scalar field, and then we can reach this simple equation for the scalar field perturbation where the effective mass is just defined in this simple way, that is just the perturbation of this term here. This looks like a wave-type equation, and clearly when the effective mass, the square of the effective mass, is less than 0, we have a tachyonic instability present in our system, leading to the development of scalar field. Okay, and how do we build a theory that actually allows this setup? Okay, so the freedom that we had in our scalar tensor theory is the choice of the potential and the potential term and the coupling function. Okay, so now let's first forget about potential because, well, at least this was the original, the Moore-Esposito-Farese model when they discovered the spontaneous scalarization. And then let's focus only on the coupling term because this is where the spontaneous scalarization is being held. Okay. What are our options? Okay, so we normally work not with with this function itself, but instead with its logarithmic derivative because this is what enters in the scalar field equation. And since we don't know how the coupling function would look like, the simplest is to take just an expansion with respect to the scalar field. Okay, so now let me remind you the scalar field equation. And let me remind you again that phi equal to 0 should be a solution of the field equation. Clearly, if we keep only this term, phi equal to 0 is not a solution. We have to keep a term like this or higher. And again, if alpha of phi is just a constant, then we have the famous Browns-Dickey theory that is specific with that phi equal to 0 is not a solution of the field equation. This means that we always have scalar field around our compact object. But the problem is with the Browns-Dickey theory is that we have scalar field not only around neutron stars, but we have scalar field around any compact object. So any presence of matter would actually induce the presence of scalar field, which means that the weak field test of gravity can also probe this theory, and that's why it's more or less ruled by observations. That's why let's forget about the first term here and keep only the second term that is linear in the scalar field. Okay, so if you remember, we're talking about an effective mass of the scalar field, that when the square is less than 0, we could have instabilities. So as you see, it depends on the trace of the energy momentum tensor and the first derivative of this coupling function. So for most of the neutron stars that we can construct, the trace of the energy momentum tensor is actually less than 0. Is greater than 0. So in most cases, the trace is greater than 0. It's a typo, and this means that the first derivative should be less than 0, which means that beta should be negative. So practically for negative beta, we have this case of standard scalarization that was discovered by the Moore Esposito Farese, and this is how our solutions look like. This is the mass as a function of the radius, and let's focus only on the solid lines. That is the case when we have static non-rotating neutron stars. Okay, so the black line corresponds to the GR solutions, and different colorful lines corresponds to scalarized solutions with different strength of the coupling or different values of beta. So practically the more negative beta is, the stronger the deviation from general relativity. Okay, so what is specific? So first, GR solution is always a solution of the field equation. So practically neutron star without a scalar field is also exists in our scalar tensor theories. But at this point here, the GR solutions become unstable, and it gives rise to a scalarized solution with scalar field, where here the scalar field grows, and then a little, okay, so here the mass grows, then a little bit decays, and merges again with the GR solution. So practically from this point to this point, that are the two bifurcation points, our GR solutions are unstable, and instead the stable, energetically more favorable ones are the scalarized ones. It's interesting to see that actually this is the static case. But it's very interesting that if we go to the case of rapid rotation, these small these small deviations from GR, at least for these values of the parameters, the deviations are small, are actually magnified much more, which means that in rapid rotation for very moderate values of beta, we can actually have very large deviations from GR, which actually is another channel for testing scalarization, because we have such rapidly rotating neutron stars forming, for example, after merger and after other violent processes. Okay, so a natural question to ask is whether one can scalarize neutron stars only in the standard scalar tensor theories, and the answer is no. It's possible to have other theories of gravity that allow for the so-called scalarization. And another such example is the Gauss-Bonnet gravity. So here the difference is that the trigger for the development of the scalar field is not that the trace of the energy momentum tensor. Instead, it is the Gauss-Bonnet invariant and the curvature itself through the Gauss-Bonnet invariant. The Gauss-Bonnet invariant is just a curvature invariant of second order that depends on the scalar, on the Ricci tensor and the Riemann tensor. I have not written a formula. The idea is that this is a quantity dependent in a way on our metric and its derivatives. So if we if we add to our action the Gauss-Bonnet invariant coupled to a scalar field, then this term here, when transferred to the field equation, this can itself act as a source of the scalar field. And in Gauss-Bonnet theory, actually the solutions look much different. So this time the mass is a function of the central energy density for neutron stars. And again, the black line is GR that always exists, and the different colorful lines corresponds to different combination of lambda and beta that are just parameters in the parameterization of this term here. So here we have actually two terms. Lambda keeps the dimensional part, and beta is the part in the exponent of the phi square. So as you can see here, what is specific first is that these solutions always have lower mass compared to GR. That is in contrast with scalar tensor theories, where it was a bit different. And also, the solutions are terminated at a certain point. That is the point where the conditions for regularity are not satisfied. Regularity in the center of the star. Okay, but still, these are also solutions that were extensively studied in the literature. Okay, what about other neutron stars beyond general relativity? If we don't want to obey the mechanism of scalarization, but if we want to just produce a neutron star in another theory of gravity, okay, so perhaps the other famous solutions for neutron star, by famous, normally solutions that are astrophysically viable and for which astrophysical implications have been studied. So these are, again, neutron stars in Gauss-Bonnet theory of gravity. But in the previous case, remember, see that our complex function had a phi squared term. So phi squared term was the one that normally helps us to have a GR solution as solutions of the field equations and scalarization happening. So if we keep only linear term, if the leading order term here in the expansion of f of I is linear, then we always have scalar field we always have scalar field on the background of GR. And in this time, actually, the solutions look very similar to the spontaneous scalarization. So they always deviate from GR, but at least for small black hole masses, the deviation is small. And then when we increase the masses, when we increase the central energy density, the mass grows. And again, we have this feature that the branches are terminated. You can ask why considering this theory and forgetting about Brown's decay theory, because in that case we also don't have spontaneous scalarization. Well, actually, it turns out that the Gauss-Bonnet theory is a little bit more special, because here the scalar field is sourced always, in this case as well, by the curvature itself, which means that in experiments when like binary pulsars and other weak field experiments, it's much more easier to hide the scalar field and not have severe constraints by observation, and still allow for the existence of this theory for such neutron stars. And here is a small subset of the neutron star models beyond general relativity. For sure, I have forgotten something. I have focused mostly on the models for which I would say that there are more models developed, and one has reached the point of actually performing time evolution or studying some astrophysical implications. This includes, for example, neutron stars in the dynamical Chern-Simons gravity. That is another version of a theory where we have a curvature invariant of second-order induction, quiescence theories, FFR theories of gravity, tensor multiscalar theories, and well, for sure there are more here, and this is people are actively working, but still, as I said, still up to date. Whenever something new and interesting happens, the first theory to test it is actually the more Esposito Farese model, because this is the best behaved model we have up to date. Okay, and what is the biggest problem when we have our neutron star with some scalar field? These are the binary pulsar constraints. Well, a problem or not, it depends on the point of view. Why? Because the binary pulsars are systems where we can actually, through pulsar timing, we can measure certain quantities of this system of two pulsars orbiting around each other, or a pulsar and a white dwarf, or whatever we have. So we can measure with great accuracy certain characteristics of the system, and we can check whether they match general relativity or not. Okay, so different characteristics of a binary pulsar system can be measured. And for example, this is here a figure of the mass of the primary to the mass of the secondary object in the binary. And in GR, all observations should give us a line connecting one mass and the other. And theoretically, all observations of different characteristics, like the advance of perihelion, the change of the orbital, the change of the orbital period, and so on, all of them should intersect in a certain point if we want to have a self-consistent theory, right? Because practically all observations of a single system should lead to one ratio of the two masses. Okay, so this is for GR, and here the theory works perfect and they really intersect in a single point, of course, up to the accuracy of the observations. Well, this is not true if we, for example, consider a scalar tensor theory model where we have a certain coupling function. I won't go into details because it's not so important. The idea is that if we allow for strong scalar field, not well adjusted to our, let's say, binary pulsar system, it might happen that this line failed to intersect in a certain point. And here the best example is PB dot, which is the change of the orbital period of the system. So the change of the orbital period is... okay. Okay. The orbital period changes just because we have emission of gravitational waves as the two pulsars move around each other. And as you can see, this change of the orbital period and the perihelion advance, they eventually would fail to intersect in a certain point, at least in this region, which means that this theory is discarded from observations. And then by taking such consideration, mostly on the basis of the change of the orbital period, then one can constrain the parameters of the theory. So remember, our action is scalar tensor theory, our coupling function that we expanded like that, and then we can take different pulsars, and different pulsars put different constraints. So practically everything that is below this line is allowed from observations, and everything that is allowed above this line is discarded. So as you can see here, the red line, it almost actually discards observation, spontaneous scalarization, because spontaneous scalarization happens for beta less than minus 4.5. And then also the alpha 0 parameter, that is the pure Brown's decay part, is also severely constrained. And what's interesting actually is that for the moment, the binary pulsar constraint give better constraints on the weak field regime of gravity, let's say, even better than the Cassini observations. Okay, so practically the situation until now is like this, that binary pulsars more or less have discarded the original, the scalarization in the original, the more Esposito Farese model. Of course, we can apply this binary pulsar observation to other systems. For example, the scalarization in Gauss-Bonnet theory of gravity. So here again we have two parameters, lambda and beta, which are connected to the coupling function. And I won't go into details. By performing analysis of observational data, one can put constraints that, for example, in this case, lambda should be lower than one of these lines, which practically also means that the stars that we observe out there should not be scalarized, because scalarized means that, okay, I should have mentioned this in the past, scalarized object or object with a scalar field means that, that normally if the scalar field, okay, object with a scalar field means that we normally have some conserved charge of the system, that is the scalar charge is seen from infinity. This scalar charge actually leads to an additional energy, to the initial additional channel of energy emission, which means that the system, when or a binary system would lose energy much faster than in general relativity, and the dynamics of the of a binary system will change considerably. So that's why we, for now, know that if we have a scalar field which allows for some scalar charge, like some conserved charge is seen from infinity, then we cannot then we are in trouble with the binary pulsar observations. Okay, so how can we go out of this? Because this means that most of the cases of scalarization are killed by the binary pulsar experiments. Okay, the simplest thing is to add a mass of the scalar field. Why this is helping? When we have mass of the scalar field, this means that the scalar field is dropped exponentially, and as seen from a distant observer, practically the scalar field is confined in some radius around the neutron star, and if this radius is smaller than the orbital separation between the two pulsars, then at the end we will see no scalar gravitational radiation being emitted and no change of the orbital dynamics. One can have also scalar, in certain theories like the tensor multiscalar theories of gravity, one can have scalar fields which drops not as 1 over r, but as 1 over r square or higher orders, which actually also effectively kills the massive amount of scalar gravitational radiation. As I have showed you, rapid rotation can allow us to have large deviations when we have rotation, but almost zero deviations when we have static neutron stars, and the pulsars that we observe are practically can be considered as static neutron stars, and so on. So there are ways to evade it, but of course one should be always careful when constructing a theory that it passes through weak field observations and binary pulsar observations. Okay, so I have just a few minutes to focus on some astrophysical implications. And let me start with the binary mergers because, well, these are perhaps the loudest events out there that we're going to observe. So the truth is that the dynamics beyond general relativity, not only for neutron stars, but also for black holes is still poorly studied because, well, these theories are more difficult and the simulations themselves are difficult. And the first study of mergers, I think the first study ever of mergers beyond general relativity was the merger of two neutron stars in the De Moivre-Esposito-Farese model. So people practically observe how, as the stars approach each other, they develop scalar field and they merge. The interesting thing here is that even if the neutron stars, for example, this star here was not initially scalarized, as the neutron stars approach each other, they develop scalar field dynamically just because this is no more an isolated system. Instead, this is a coupled system of two neutron stars. And the same problem was studied later in much finer details in another paper. And it turns out that this is the evolution of the scalar field as a function of time. It turns out that we can have spikes of scalar field development. For example, this time here is more or less the time during merger, happening shortly before the merger, or during merger that can potentially have strong observational implications. Of course, we should not forget that it's not only the Moivre-Esposito-Farese model, but we have other theories of gravity which have interesting neutron star solutions. For example, the Gauss-Bonnet theory. And here also it turns out that if we perform the evolution of two neutron stars, again, scalar field can develop dynamically and magnify during merger. The problem with this theory of gravity is that the moment when we deviate from the simple, the Moivre-Esposito-Farese scalar tensor theory, another scalar tensor theory as well, we end up into problems like well-posedness, loss of hyperbolicity, and so on, which is a very unpleasant problem, but it happens in most complicated theories of more complicated theories of gravity that I'm aware of. And for example, this is here the waveform produced in GR, alpha equal to 0, in another flavor of Gauss-Bonnet theory, and the waveform for another specific for value of the coupling function. And this is, as far as I remember, this was more or less the maximum possible to perform simulation without encountering severe problems coming from the theory. And as you can see here, even though there are differences, they are not dramatic. So it's not so easy to deviate dramatically from general relativity. What I would like to advertise you in the last 2 minutes is what about, okay, so here what people were normally looking at is, let's take GR, let's take another waveform, and they'll have tiny shift one with respect to the other, and let's see if we can actually measure this through gravitational wave observation. But what if we actually have some qualitative difference between GR and another theory of gravity that give us a completely new feature that we can explore in a different way that is not degenerate with the equation of state uncertainty or other uncertainties in the model. And okay. What I wanted to tell you about is the so-called gravitational phase transitions. Okay, I think that at least yesterday there were some words about phase transitions for neutron stars, that practically if we have a neutron star made of the nuclear matter, if we choose our equation of state in a specific way, we can make a phase transition to another state of a neutron star with a quark core that is another branch of stable hybrid stars. It turns out that very interestingly we can have a similar setup with similar phase transition happening for neutron stars. So if you remember, this was the picture for the neutron star scalarization in the Morse-Positano-Farese model. So the blue line were the GR solution, and the yellow line are the scalarized solutions. So the scalarized solutions are nice stable. They are the only stable. Here the blue line is unstable. But after the maximum of the mass, this portion of the branch becomes unstable because maximum of the mass, independent of the theory, is normally a trigger for instabilities. So imagine that we have a star here and we have some mechanism to climb upwards and to reach the maximum mass. Then the next moment, the star cannot reach down, cannot go down, right? It can also not go somewhere here because this branch is unstable. Instead, the star would transition from here to the GR branch. That is actually very similar to the first order phase transition for neutron stars. Okay, I'll try to be fast. Okay, so and how this happens? So one can take a star and artificially create scalar field, and then okay, so this is the same picture like before, but just this region here is magnified, and then eventually the star would transition from here to this branch, and this branch is the GR1 with zero scalar field. So practically, it would emit completely its scalar field. So clearly, this is a huge change because the star reorganizes, it emits scalar gravitational radiation, and this is something that we can potentially more easily trace in the observations. And if we choose our theory wisely and if we allow for certain couplings, then it turns out that we can actually have a relatively strong gravitational wave signal through the so-called bridging modes emitted during this process. The trick here is that you remember that I told you that the Morse-Positano-Farese model is ruled out by binary pulsars for the moment. That's why we need to modify it somehow, and the simplest is to just add a mass of the scalar field. Well, adding a non-zero mass of the scalar field means that we'll have this dispersion relation for the gravitational waves, which means that gravitational waves with different frequencies would arrive at different times. And that's why instead of having a spike from this emission of the scalar field here, from the transition of here to here, we'll instead have a continuous signal lasting for years. And the good thing is that, okay, if we take a very moderate guess for an object out there at 10 kiloparsec, it was around 2 solar mass neutron star, then the emitted signal, this continuous gravitational wave signal, is inside the sensitivity even of advanced light. But if we go to a little bit more conservative choices of the distance, we'll certainly still be above the ET or cosmic explorer sensitivity. Okay, so you can say that this is too small because we are interested in mergers. No, actually we are here interested not only in mergers, but certain processes can also happen through core collapse, through accretion of matter of a neutron star. We just need a way for the star to climb from here to here. That can happen in other processes happening in our galaxies that are much more often. And see, this signal here lasts for years, not just for milliseconds. So theoretically, we might be able to see such continuous gravitational wave signal from events happening even 100 years ago. Okay, so this was the last talk. Thank you very much. Conclusions. I'll skip them. Thank you.
Thanks, Daniela. Okay, do we have any questions? Okay, a few. Yeah, go ahead, EJ.
Thank you.
I can hear.
Let me pause you this one. I'm coming.
Yeah, thank you very much for the talk. For the you mentioned that the EOS uncertainty will affect this test of gravity. So how does this actually affect your test with the Gauss-Bonnet theory? Because you showed the constraint from Gauss-Bonnet theory. So for the equation of state, the uncertainty will affect the constraint on the testing gravity. So how does that happen in your Gauss-Bonnet theory?
uncertainties in the matter equation of state affects everything. It affects the modeling of the objects, it affects the astrophysical implication, it affects the gravitational wave emission, and you always theoretically want to find something that is above the equation of state uncertainties. That is not that easy. Or you hope that the question of state uncertainty will be cured one day, which is another questionable moment, whether you can cure it in a model-independent way. Or the third way is to, like what I have shown, to try to find something that is more specific to a theory of gravity that cannot be easily mimicked by question of state uncertainty. But yeah, but still, I mean, I think you know, you also work on this. Still, what I was putting in the conclusions, even though we have this matter uncertainty, still for the moment, some of the best constraints of GR are given by neutron stars. So even if we think, okay, they're terrible because of this uncertainty, yeah, they are terrible, but there are so many observations that we still can pose much stronger constraints on a number of theories of gravity compared to black holes, black hole modeling.
Okay, so for your constraint, you have assumed one equation of state, right? Or you have
here? You mean here or
the one before? The one when you put a constraint from binary pulsar on.
Okay. So you talk about the yes, binary pulsar.
Yes, one.
Okay. So I have removed this picture in the morning. So different pulsars here give different constraints, and for Gauss-Bonnet gravity. It's not like the more expositive Fourier model. We need the more massive pulsars gives a stronger constraint. So we need more and more massive. And the equation of state, I can show you later the figure. It also changes a lot the constraints. Still, we can say that even if we take the most massive pulsars and if we take a very broad range of equations of state, we still reach, I think, the maximum that we could reach is that lambda should be less than 20. So there is uncertainty, but still what we get is still much better than what we get from, for example, neutron stars for the moment, or than black holes for the moment.
Okay, we have one more question up here.
So thank you for the nice review. I would like to ask you about, again, constraints. So you talked about constraints coming from, well, binary pulsar and maybe the mass radius diagram. You can put constraints from there. But you can also put constraints from tidal love numbers, for example. Mm-hmm. And I suppose that you worked on that even. Can you tell us something about what you get, what kind of constraints you get for the more esposito Freise from that, if you modify it with a mass term to avoid the binary pulsar constraints, perhaps? Thank you.
At least to my knowledge, constraining the theory directly based on the tidal deformabilities is, I might be mistaken, but I cannot recall a paper that constrains the theory just based on the tidal deformabilities for modified gravities But then I think that it comes the next question that I think we discussed a bit yesterday. So you can believe tidal deformability. I mean, if you want to constrain only tidal deformabilities, I mean, you cannot take tidal deformabilities for granted, because these tidal deformabilities are extracted with GR waveforms. And you say that, okay, my tidal deformability should be smaller than X, okay, but you haven't matched your gravitational wave data with your template in modified theories of gravity. So at least in my opinion, what is more important is to actually manage to come up with a template that matches well the modified theory of gravity, and then let's see whether we can make constraints from there, because blindly taking deformabilities from GR and transforming them to neutron stars, in some cases, to modified gravity, in some cases it might work, but in my opinion it's a bit dangerous to just blindly start from there without any data analysis.
Okay, I think we can have one quick question, and maybe, David, you can set up for the next talk.
Very naive question about the nature of the phase transition you talked about in the last part of your talk. Is that a first-order transition? Is there a large-scale reorganization of the scalar field necessary to go from one configuration to another?
Yeah, this is the point that this is actually a phase transition of first order, and that's why it's so nice for the observational prospects, because it actually happens with a jump. So one jumps, is this working? Yeah. One jumps from here to here, which means practically, so this here happens on dynamical timescales. In our case, I think it was a few tenths of milliseconds, and practically very abruptly the star changes its properties, and then all the scalar field is emitted. So this is phase transition of first order, if we make an analogy to matter.
Okay. Okay, I think we'd better, leave it there, and we can always chat in coffee or in the Slack channel as well. Let's thank Daniela again.